We're going to cover energy methods now. Energy methods is a very cool way of solving various problems when it comes to mechanics and materials, beams under loads. It's a really nice way of tackling problems in a way that can make things easier for you. So let me talk about that. It's actually pretty neat. I actually enjoyed very much energy methods. In fact, there's a follow-on course that really goes into that in a lot more detail. So here we have a uniform rod that's loaded on the loading conditions here. As you can see, it's an axial load. Anytime you apply a load to a structure, that structure is going to contain some amount of strain energy stored. And when you apply a load to a structure, there'll be work done due to that load applied. And so in this case, what I want to cover now is a few examples here about that. I'll just go here and show you that if I plot the load versus deflection here, the energy under this curve is the energy due to the work done due to the load applied. And in this case, if the loading applied was linear, then the area under that becomes the area of a triangle. So you get 1/2 times the load P times the deflection X. So that'll be the work done due to that load. So here you can see the example of a load versus deflection on the bottom left. And what you see here is that when I apply a load to the system, it could react linearly as a function of the deflection. And that area under the curve is 1/2 the load P, which is the height of the triangle, and X, which is the base of the triangle. So that's the energy due to the load applied. You can also write it in terms of the spring constant, so that bar is going to have some sort of stiffness. If that stiffness was K, then you can also rewrite this equation in terms of K. That gives you 1/2 K x1 squared. You wonder where the K came from, or this equation came from. If P is K times X, which is this is a slope K, P is a load. If the load is equal to the stiffness times X, then you can plug it in here and you get 1/2 K x1 squared. So there's two forms of the energy that's applied to the system. And then at the bottom left, what you see here is a strain energy density. So let's focus on the equation on the bottom. So the strain energy, let me see if I can use a pointer here. You can see here. So I have the strain energy. The strain energy is the integral of the modulus times the strain d epsilon x. So this is a plot of stress and strain. If you integrate this relationship, you get the area under the curve, and that's the strain energy per unit volume. That integral then, if you were to do it for a triangular, like a linear behavior here, you'll get that the strain energy is 1/2 E times epsilon squared divided by 2, or it is equal to sigma squared divided by 2 over E. And if you're wondering how I did that, I can just do it for you quickly. So this is stress, this is strain, that's your relationship there. And then the area on this curve is what? 1/2 sigma times epsilon, but sigma is E times epsilon because of the constitutive law times epsilon. The epsilon is this one here. I get 1/2 E epsilon squared. You can see that relationship here, and you can also rewrite the relationship in terms of sigma, and when you do, you get this equation here. So all these expressions are similar to each other. I apologize to recovering. So yeah, so if you were to look at the strain energy for a bar on the loading conditions, so you have this bar here that has a load P applied. I can do a free body diagram. And what you find is that the stress is P over A, right? Stress is P over A. So if I do a section cut anywhere in that bar, I find that the internal load to the bar is P, right? So if I apply an external load P, and I do a cut inside the bar, what is the reaction force in that bar? P, correct? So what I can do then, let me show you how to do this with a different ink, because red can be dramatic, right? So sigma x equals P over A. So you do a cut there, I apply a load P here. If I do a cut there, then sigma x equals P over A. But I can then plug in P over A into this equation, the strain energy equation that I had just derived earlier. And when I do that, I get P squared 2A over E. I think you can all see that that occurs. Does that make sense, this equation here? Yeah? There's many ways to get this equation. So for example, one way, I told you the area in the triangle is 1/2 sigma epsilon dV, right? But another way is to say that epsilon is sigma over E. And when you do that, you get sigma squared divided by E, which is exactly what you see there. So you can actually get from this expression, the energy under the triangle into that expression for that integral. And if you plug in the load, the stress equals P over A, you get that the strain energy is this much. Now for constant cross section A, obviously A and E is constant, so they do not depend on dx. So now this integral becomes P squared 2E over A integral 0 to L dx. And what is the integral from 0 to L dx? L. So the energy then becomes, and I have it here done already. So let's clear the ink. I didn't do, oh, there it is. P squared L 2EA. So that's the strain energy stored in the system, inside the system, due to that load applied P. Any questions on this topic so far? Again, let me simplify for you. When there's a system and there's loads applied to that system, there'll be strain energy stored in the material due to that load applied P. And in this case, the energy was calculated as U equals P squared L 2 divided by 2 times EA. Any questions on how I derived that equation on the bottom? Well, the bar in question can only develop strain energy when a load is applied, right? Because if you don't apply a load, do you agree that there's no strain? If there's no strain, there's no strain energy. So the deformation only occurs because you actually applied a load. So you cannot get any strain energy if there's no load applied. So
like the load applied for a little bit versus like a long time, it's still the same.
In this case, you have a good question. So we're not accounting for dynamic effects. We're assuming that the loads applied are time independent, but there are ways to account for time dependencies, and that's covered in a more like a dynamics course, and where we bring Hamiltonian principles for dynamics. I covered that more in a more advanced course, for example. For inelastic strains, then in that case, let me take an example for inelastic strains. I love that example. I covered that more advanced course, but since you're asking me, why we don't kind of show you what you will do in that case. So stress in that case probably can be approximated as something that looks like this. Okay. In this case, what is stress? Stress equals, I don't know, I'm gonna have to make it up. K square root of epsilon maybe, or K is some constant that you figure out that matches the stress strain curve of the material. That's inelastic, you agree? Or non-linear, not necessarily inelastic, but at least it's non-linear. And you can then integrate that. So you will integrate K square root epsilon d epsilon dV to come up with a strain energy due to that non-linear behavior. But again, that's covered more in advanced course. But for the purpose of this class, we're going to assume it's a linear behavior where stress is equal to modulus times strain. And if I make that assumption, then the energy under the curve is sigma squared, the stress squared, divided by 2 times the modulus, which is the formula you see right here. And I derived it for you two different ways now. Okay? Does that make sense to you? Do you want me to derive it one more time so you guys can see it visually? I can do it quick. Some of you say yes, so let me just do it quick. So this is the stress strain curve. That's the slope, E, right? What is the area under the curve there? What is the area under the curve of that stress strain curve? 1/2. So the energy is 1/2 sigma, the stress times epsilon, correct? Now you can write this in terms of stress, or you can write in terms of strain, right? So what is strain in terms of stress, as an example? So strain is equal to stress divided by modulus. You agree? That's one way. So that's 1/2 sigma squared divided by E, which is exactly what you see there. We have multiple ways to write the formula. You can write in terms of strain, right? That'll give you 1/2 modulus times strain squared. Okay. Multiple ways of doing it. Okay, let's move on, right? We have material to cover. For bending moment, if you have a bending moment, I want to derive I can derive some of the formula here fairly quick. Do you remember? So when you have bending moment alone, so you have bending moment, does everybody agree here that stress is equal to ny over I? Do you remember that formula before? We covered it, right? So what if I plug in stress in here? When I do that, I get integral m squared y squared 2ei. You agree? You agree so far with that formula? Yes? Can I write this as integral of m squared? No, hold on. I'll make it better there. So I'm gonna say moment is constant for a second. It's not constant. Or actually it's not constant. So let me just do it this way. I'll do integral m squared over 2ei dx y squared dA. So I'm going to break up my integral into two pieces. This does not depend on the cross-sectional area, say. And the integral, and this double integral here, double integral y squared dA, I believe, I'm missing a squared here, by the way, it's I squared. 20 points for you for picking that up. I could read. I saw you say, oh, I already knew. 20 points for you. I squared, right? So you have there I squared. So I squared, I squared here. The double integral y squared dA is really I, and one of the I cancels with this I. And so you will get the expression I'm going to show you in a second here. Let me give you a minute so you can type this. Yes, the strain energy for most problems is going to be like that. Yeah. But in a more advanced course, if you take it with me, you'll see that it's a more complicated expression. But for this more advanced, this is still an advanced course, but not as advanced as a graduate level course where we cover the more complicated strain energies. Where we can have, let me go off the record on this literature. Let's just keep it simple. I think it'll be very appreciated. So let's look at this. Everybody has typed this now. Before I erase it, everybody's on board with me? You follow me? Okay. So there you go. That's the equation I just derived, n squared over 2ei. And if this is fun. This is fun. Let's check this out. Let's check this out. Have anybody looked at the solution of a cantilever beam under N load applied? Under that load applied. Has anybody looked at that before? You can look it up in any book. It gives you the solution. So if I do a cut here, let me do a cut right there, okay? I'll make it very excessive so you can see it, okay? Okay, that's very obvious. If I do a cut there, what is the moment in that cut? And the cool thing about energy, I can use my coordinate system anywhere I want. I can place it anywhere I want. I'll make my coordinate system start from here. This is x, okay? So if this is my moment that gets formulated there, what is the moment inside that cut? P times x, correct, very good. 20 points for you again. So P times x is what goes there. The moment is P times x. So moment squared is P squared times x squared. You agree? That's what I did there. I put moment. And do I care about the sign convention? I hate sign convention. You hate sign convention. I hate sign convention. Mormai, she hates sign convention. Sometimes we're hours talking about sign convention. We're discussing because in different parts of the world, they use a different sign. In civil engineering, they use a different sign convention. Where I learned from a different sign convention. We have all different sign conventions. Cool thing. What happens to a negative sign when you square it? It's gone. Do I care about sign convention? No. That's the beautiful thing about energy. It's squared. So you can be wrong about the sign, but yet you're going to get a great answer. So here you can see that strain energy is P squared S squared divided by 2EI. What is the integral of that? That integral is P squared L cubed over 6EI. And moreover, and I'll cover this later, but just for fun, this is equal. What is the work done by this load applied? 1/2, 20 points for you, 1/2, kind of, 10 points because it's really 1/2 in front. 1/2 P times the vertical deflection, correct? Didn't we cover that just a minute ago? We said that the work done can also be written in terms of load applied times the deflection divided by 2. That's the work done by the energy, right? By that load, sorry, not the energy, right? Does that make sense to you guys? Yes? So if I want to find the deflection, don't I have to equate this to that and I'm done? You can equate the work done to the strain energy. And guess what happened? I can calculate the deflection there. What is the deflection? The deflection becomes, just do it yourself. You're going to see it's going to be PL cubed over 3EI. Beautiful. Go. I don't understand what that means, but I can tell you this. I apply the load downwards, so the deflection is measured downwards. If I apply the load upwards, then the deflection is measured positive upwards. In this case, in this example. But you can choose your sign convention. That's a beautiful thing about energy. Does that make sense? Can somebody Google for me the deflection for cantilever beam under load applied? Just type that very quickly. Deflection of a cantilever beam under load applied. What do you find? $20 points for you. Does that match what I have here? Except for the negative sign. Probably because I don't know what convention they're using. Correct? They're probably looking at deflection moving upwards, not downwards. Mine is going downwards. Isn't that cool? We used energy. Did I use the elastic equations, like the EI, Y4 primes equals 0? Did I have to integrate that 4 times to get an answer? No. How did I do this? So cool, huh? I love this technique. Okay, and I have used this. It's amazing. You can also, I don't want to replicate this again, but for torsion, just for torsion, just to give you the formula for torsion, the total strain energy for torsion is tau squared divided by 2G, where the shear tau xy is a shear in the xy plane squared divided by 2G. And then if you plug in the formula for shear into this formula, okay, you're correct on the chat. Good observation. Now I can plug this in here, and then what you get is that for the strain energy for a torsional load is this. So for bending is what I had shown in the previous page, but now when you apply torsion, it's torsion squared. G is a shear modulus. J is a polar moment of inertia. And if I apply a torsional load for something that's length L, just uniform, the strain energy becomes that. Make sense? I can do the same thing where I equate this to 1/2 torsion times phi, how much rotation you get from the load application. But I won't do it here. I'll cover it coming up. Any questions you have on what I've done here, please? You can superimpose, beautifully said, 20 points for you. You can superimpose different solutions for different problems. As long as everything is linear, you can superimpose them. And the stress, when you add them up, the stress does not exceed the yield of the material. You want everything can be added as long as you're below the yield of the material. Okay, please.
Kind of follow the question. So if there's like a case where it's like torsion and like a load applied, you just add up.
Yep, I'll show you that. I have an example. Excellent. Very good. So I think I derived this equation already. P squared L over 2EA for a load applied like that. I already derived that for you. I already derived that if you apply a load P, you also get the work done as 1/2 PX. I already did that for you. This is a summary slide. You agree that I covered all this? Can we sign a contract saying that you agree that we covered this? Yeah, you agree? Make sense to you? Does it make sense to you? The delta symbol here, I don't see the delta symbol here. I don't see one. Like this one here? This one? I could have used a different variable. I could have used, let's say I could have used this variable, say. Say I could have used W. You can use whatever variable you want, as long as you know that's the deflection where the load is applied. Hopefully that answered the question. And if not, please email me or put in Piazza or ask the question now so we can hear you. But I think we got it. Okay, very good. I already covered this. This is a summary slide. We can move on. Okay, what's going on here? There you go. Okay. So let me go one by one. So on the left side, what you see is a transverse load, what the energy is for that. I already derived that for you just a minute ago. P squared L cubed divided by 6EI. I derived the one for the bending couple. I did not derive the one for bending couple, but that's very easy to derive. You get M squared L divided by 2EI. And that's a very easy thing. You know, you apply a bending moment at the end of this beam. And if I do a cut here, you agree if I do a cut here, the bending moment internal to that is M also? Yeah, you agree? So let's look at the formula for energy. Energy equals integral N squared over 2EI, 0 to L, dx. Let me ask you this. What is that integral? So M, if I apply load M1, then if I do a cut here, what is the moment there that balances that? Negative M1. But do I care if it's negative? I hate science. M1 squared, isn't it? M1 squared over 2EI dx. You agree that modulus is the same everywhere? This is not an additive manufacturing material, the modulus changes. You agree this is a constant cross-section? So I is constant through the length? Is the moment M the same everywhere through the length? Because it doesn't matter where you cut, you get M, right? So all this is M1 squared divided by 2EI 0 to L dx. What is the integral 0 to L dx? L. So that's what we got there, M1 squared L divided by 2EI. There you go, done. Does that make sense to you guys? Torsional couple, if you apply a torsional load, you get that the energy is T1, the torsion applied T1 squared L divided by 2GJ. G is the shear modulus, J is the polar moment of inertia. By the way, the polar moment of inertia is provided to you for a lot of different geometries in a lot of different books. Okay. Any questions on that? Shall we move to some examples then so you can see how this works? Why not? Now, what I want to do, I don't want to spend too much time doing some procedures that were done in statics already, but I want to focus on what this particular lecture is about. I think everybody agrees that if I had a geometry as shown here, what I can do is if I want to calculate the strain energy of this structure due to a single load, as you see there, a load P applied, I want to figure out what deflection occurs at that load P, okay? And that's something you may not have seen before, but we can do it with the methods we discussed. What do you think is my strategy to determine what is the deflection at that point? Anybody has a strategy that you think is going to work? Kind of. Energies can be added. You agree that energy can be added? Yeah. positive vibes plus positive vibes equals what? It's a trick question. Positive vibes, good energies, right? Negative energy plus positive energy, what does that equal? No, you don't know the answer. Because what if it's more negative than positive? Or more positive than negative, right? What is negative vibes plus negative vibes? Negative vibes. So what is the best way to live life? Positive vibes. Is it possible to always be positive vibes? No, why? Sometimes it sucks to kind of live life, that particular day. Maybe you didn't eat all day long, right? Do you want to pass that negative vibe to somebody else that does not deserve it? So what you should do to tackle it? I thought 20 points for you. That's great. What you should do, you should probably maybe meditate, take some time to like relax a little bit. Maybe step back and look at life differently, right? Sometimes we're digging a hole and we don't see where life is going. Sometimes you want to step back and kind of look at things from the big picture perspective. First of all, you can breathe, you can eat. Maybe you cannot eat, but okay, that day you couldn't do it. But play basketball. You're trying to get more points, but I do like basketball. I do owe somebody basketball here. But bottom line is you want to keep a positive attitude. So I really think that you want to be like these beams, these trusses here. A lot of positive energy. These are all positive energies, by the way. So when I apply a load P, this bar is going to stretch, you agree? And this bar is going to do something also. Even though it's going compression, it's not negative energy, by the way, it's positive energy. So both of those bars will produce strain energy, 1 and 2. And that load P, what does that load P does? It produces the work done, right? So what is the work done due to that load? Correct? And what is my goal in this problem? Find that deflection. That's what I want. So all I have to do then is to calculate the energy in bar 1 and bar 2 in terms of P. And if I do that, I can equate it to this and solve for deflection. You agree? Is that a good strategy to solve this problem? Do you understand how this works? When you apply a load P, there's a strain energy that's going to be formed within the body of the material, and that's going to be equal to the work done due to the load applied P. That's how they work. So to remind, I'm not going to go back to statics and show you how to get those forces. I think everybody knows how to do a section cut there. Remember how to do that? The method of joints. So you take that point B, right? You have a load there, right? You kind of remember this or not? And this was what? FBC, FBD, right? And the load applied downwards P. I'll let you do it. Summation forces in X, summation forces in Y equals 0. And then you could then find that FBC, the force inside bar number 1 is 0.6 P. And you will find that force in section BD is 0.8 P. Does that make sense to you? I'm not going to do it here because that was covered in different class. But hopefully you follow the process. So what did we say the energy was inside a single bar? What's the energy in a bar? I have it right here. Force times length divided by 2EA. That's one formula. There's various formulations of this. But how many bars I have? I have bar 1 plus bar 2, right? For bar 2. You agree that the length for bar 1 is different from bar 2? And I give them here just for your information. So this length that goes here is different. The length that goes here is different. What about force? Is the force different for bar 1 than force bar 2? Yeah, I got them here. You see them here at the bottom. They're different. What if in the exam I decide to give you this problem again, the same problem. I give you the same problem, and I tell you the area, the cross-section area for one of these is twice this one, what will you do? You put A, and then you put 2A. You agree? Does it make sense? But somebody's going to email me and tell me I was unfair because I did not explain this in class. Somebody's going to do that. Guarantee you that. So you agree that if this cross-section area is A and this 2 times A, all I have to do is plug it in here and I'm done. There's multiple ways to write the same formula, right? I showed you a few ways of doing it. That's the strain energy is also this, right? I derived it. I can look it up here again. Let me see where it was. Here it is. P squared times L2 divided by EA. And what do I have here? Oh, there's an error. Is that an error? It's supposed to be squared here? Is that what your question was? 50 points for you. Great eyes. Good eyes. F squared over 2EA times L. That was the formula we derived earlier, right? Good job in catching that. The good news is that I did it correctly in my slide. So I should have just gone with that, right? But there you go. F squared times L divided by 2EA for bar number 1. For bar number 2, guess what? I know all those numbers. I know all of them. And I know that the energy has to be equal to 1/2 P, the deflection, times the load P. So don't I all have to do is solve for Y and I'm done? This is cool. I don't know how else you will do this problem if it was not due to energy. Do you have another way of doing it more cool? This is cool. Do you like it? It's a really cool method, right? I don't know. Energy is cool. It is a good technique. Any questions on what I did there so far before I move to the next example problem? This is very exciting stuff, guys. It's extremely exciting to be able to do something in a simple way that's just easy to do. You don't have to complicate your life, right? I didn't quite follow you. Why is it the deflection that we have? Now, somebody's asking me why is 0.6 cubed and 0.8 is cubed? I don't know. It shouldn't be, right? Oh, these lengths do something and then, yeah, because the length was 0.6 maybe. Yeah, I think it has to do with that. I'll let you do the math. I'm not doing it here. But you get the methodology though, right? That's what I care about. And then at home, you go and replicate it. Every example I have in my notes should be replicated by you by hand. That's the way you should be learning is take the examples I have, repeat them, and see if you can get the same answer, right? That's how you learn. Any questions you have, please. You choose. So I apply the load P going downwards, so I'm going to measure it downwards to make it easy for me. And if the load is going downwards and if the deflection is going downwards, the energy is positive. Now, if I say that this is going upwards, then this should be negative 1/2. I rather keep it all the same direction and it's easy for me. You agree? Oh, somebody's answering my question. Why is 0.6 cubed? 0.6 appears once for the length and then 2 more times because the force is squared. Bam. There you go. That's the answer. Amy, 20 points for you. Okay. Great. Thank you for saving my life because I did not know where it was coming from. Okay, good. Let's move to, okay, this gives me a headache looking at this. But can you do it? With this method, isn't this method easy? What do you have to do with this method? $20 points for you. I use the method of joints and I apply a load P here. Leave it as in terms of P. Don't change it to 40 yet. Find the load in each of these. This one, this one, this one, this one, this one, this one. How many of them are there? 1, 2, 3, 4, 5, 6, 7 even. There's like 7 little bars, right? You're like a little bit worried that this may come up in exam. Do not worry. 7 bars, right? 7 bars. I need to find how many energies then. 7. What? Sorry. Getting over a cold. No COVID. Good. Sorry about that, guys. Apologies. Okay, find the load in each of these bars as a function of P. Can the energy be added? So I add the energy for all 7 bars. And what I'm going to equate that to? 1/2 P times the deflection Y, 20 points for you. And the way this works, you can add it to your homework when you submit it. That's one approach to make it easy for my TAs. So what I'm going to do here, I'll just walk you through it. So what the first step is to do a quick free body diagram to find the reaction forces. I'll let you do that at home. We're not doing that here. That was covered in a different course called statics. But if you want to review that, I do have YouTube videos that go into statics and how to do the method of joints as practice. And then you go through each joint. I did joint E first. You can see it there. Again, I'm not going to repeat this. This was done in a different course. Then I did point C. Then I did point D. Then I did point B. And what I did, I calculated the force in each of the bars that we have in this system. So I calculated forces in AB, in CD, in DE, in AC, CE, and AB, all of them, okay? Does the process make sense? So using method of joints, calculate the forces in each of the bars in terms of the load P applied. And then what you're gonna do is calculate the energy due to these 7, all these different bars, 1, 2, 3, 4, 5, 6, 7 bars, all 7 of them. And so you can create a table, is what I recommend, a quick table. You know the force in each of the bars because you did the method of joints. You know the length of each of the bars. You know the area of each of the bars. So is it easy for you to then calculate F squared divided by times L divided by A? Is that difficult or easy? Easy, right? And then you can take all that information and put it here in this formula. So add the strain energies for each of the bars, add them up, there's 7 of them. And that gives you a strain energy of 1/2 E 287.00 P squared. Bam, done. What is this equal to? The work done due to the load applied. You told me. What was it? 1/2 P times the deflection U. Whatever, you can choose your variable. What's your favorite variable? Give me a variable that you like. I did not expect that, man. So 10 points for you on that one. Rho. I think that's the first Greek letter I used in this class. Okay, so rho, and then now I can solve for rho. I don't like that variable. That's density, man. Okay, we'll just deal with that. So yeah, density it is. So we solve for rho. You got me there for a second, huh? There you go. I did it here. I did it with y, not rho, but you can do it with rho. And the deflection gives you 16.27 millimeters going downwards. You can also have different modulus. I could tell you in the exam, oh, listen, this bar and this bar have a modulus of aluminum, but this bar and this bar are steel, for example. Then what will change in everything I did? Where? In what calculations? Where will you change anything? Huh? Where I'm adding them up, 20 points for you. You put the modulus here, EI right there. So every single thing has different modulus now. This is cool. You can have different lengths, different areas, different modulus, and I can tell you using energy what the deflection was at that point. And I don't know of other methods that can do it so clean, okay? Except for finite elements. If you take my course in finite elements, you will see that this is done in even an easier way. Please, question from you. That's an excellent question. This is an excellent question. Can I find the deflection anywhere else? I'll cover that. And I'll show you the method. It's called the method of Castiglianos. What we're going to do, we're going to put a fake load that equals to 0. It's weird, but you apply, say I want to know the deflection in point C here, where I circled it. And I'm going to apply a fake load here, Q. We call that a dummy load because it's fake. And then you do all your calculations, assuming that load Q is there. I won't show it here, but you'll see how we're going to do it. It's kind of cool, actually. Okay, great. All right, that takes me to Castigliano's theorem.